Are you tired of having to do work around your house? What about work around your office? And those tricky relationships require work too. Well, with our new product, you can forget about ever having to do work again. Introducing Work Begone.
But what's a work begone anyways?
Well, listen carefully and I'll tell you, little. Work Begone has patented anti-work technology, which soaks up all the work and places it somewhere else where you don't have to deal with it. Get rid of that pesky housework. Forget about all those work projects. Say goodbye to all that work and relationships. Work Begone takes all your work and says, hey, I'm not going to deal with you. Just listen to our satisfied customers.
Thanks to Work Begone, I hardly ever do work anymore. I guess you could say I've really turned over a new leaf. Thanks to Work Begone, my relationship ended. Yay.
With this special offer, Work Begone could be yours for 5 low payments of just $99.99 plus shipping and handling.
Wow, that's a great offer.
I know, right? OMG. So call now at 1-800-I-AM-LAZY. That's 1-800-I-AM-LAZY. Let's put work in its place. Work Begone.
Well, that's not correct information about what scientific work is. What do you think work is? Scientifically, that's not quite correct. Looks like we better get to learning.
If you got science problems and you don't know why you don't understand and you wanna cry, don't fret, my friends, because it's time for Fly Sci with Miss Sontag. It's Fly Sci with Miss Sontag. It's Fly Sci with Miss Sontag. It's Fly Sci with Miss Sontag.
Oh, hey, didn't see you there. So today our topic is work. But what is work? Is it lifting a heavy object? Is it reading a book? Is it walking with a briefcase? Take a moment to pause and write down on your worksheets A, what you think work is in the scientific sense, and B, if you think all of those or any of those situations I just listed are work. I'll give you a few seconds and I'll play some really boring music while you write. And we're back. So which of those situations did you think were work? Or did you think all of them were work? Well, before we get to that question, let's define work as scientists, or rather physicists would define work. So for scientists, the definition of work is energy transferred by force over a certain distance. So in order to understand work, we have to understand force and energy. For now, let's focus on force. So what exactly is force? It's actually not the ability to move things with your mind. Force is actually defined in physics as any interaction that will change the motion of an object. In other words, it's a push or a pull. Force is also defined as mass times acceleration, which is why we're able to write the equation F equals ma. Now why does that equation look so familiar? Oh, look, cookies! Man, I just love Fig Newtons. There's a Figgy and Newtony. Newton!
We interrupt this program to give you a very special review of Newton's laws of motion. In universal motion, Newton-based offenses are considered especially heinous. In Austin, Texas, the dedicated detectives who investigate these vicious felonies are members of an elite squad known as the Special Forces Unit. These are their stories.
Dun, dun.
Oh, Liv, it's horrible. Just despicable. Every single one of the laws of motion broken. Show me the damage. You see this object right here? It tends to stay at rest. Even when acted upon by an outside force? Yeah. What was that noise? Did you just hear that? Let's go. This object right here tends to stay in motion, despite all of our outside forces. Okay, seriously, are you not hearing that? And look at this graffiti. Absolutely a disgrace to Newton. Look at this. This is just heinous. I can't believe I've never seen anything so horrible. Okay, seriously? There is that noise again. I can't deal with this. I'm out.
Okay, not quite like that, but yeah, Newton's laws are what govern universal motion. So yeah, Newton's laws are pretty great and all, but what do they have to do with us cool kids? Well, I'm glad you asked. Watch closely and I'll show you.
As you can see here, I applied an outside force to the ball, making this object at rest move. And if you notice here, I made a mass accelerate with this force. And right here, there was an equal and opposite reaction as the white ball hit the red ball, and both bounced back.
So yeah, I guess you could say science is pretty cool. Now, I know that we're talking about work, right? And in order to talk about work, we had to make it all about force first. So why the heck am I talking to you about distance? Well, let me show you something. That's right. Just do a few little calculations here. Go away. Ha-boom! Force times distance equals work. Mind blown. So work is actually equal to force times distance. So in order to calculate work, you just multiply the force used on the object by the distance that the object traveled. Remember how I brought up that bit about Newton and the forces and motion? Guess what force is measured in? Newtons. Mind blown. So let's go back to our ball and distance demonstration. In slow motion.
So let's say I applied exactly 0.1 newtons of force on the ball and it moved 15 centimeters before it struck the other ball. So in order to calculate the work, I first have to make sure everything's in newtons and meters. So we convert 15 centimeters to 0.15 meters, and then we multiply 0.1 times 0.15, and we get 0.015 newton meters of work that have been done.
Now that is actually a very small amount of work done. But if you think about it, it makes sense, because I applied barely any force and it went barely any distance. So now that we learned more about force, distance, work, and motion, let's go back to those first 3 situations that I had you decide were work or not. Let's look at the first instance of picking up a heavy object. There was force applied to the object and it moved a certain distance. So yes, work was done on the object. Now let's look at reading a book. There's no motion occurring on the book, so there's no distance that the book traveled, so there's no work being done on the book. Now let's look at our last instance, carrying a briefcase. There is a force on the briefcase and there's distance on the briefcase being traveled. So it seems like there's work being done. Well, surprisingly, there's not actually any work being done on the briefcase. Mind blown. I know it seems like it doesn't make any sense, but let me introduce to you another little caveat about force and distance and work.
If a force is perpendicular to the distance, that means 90 degrees to it, no work is being done on the object by that force. There's a lot of mathematical explanations for this that you'll learn later in high school, but for now, just trust me, there's no work being done on this object.
So let's look at the situation up close. If I picked up the briefcase, there is work being done on the briefcase. As you can see, the force and the distance are in the same direction. However, if I start walking with the briefcase, the force is in this direction, but I'm going this direction. So there's no work being done. Now let's play that back in slow motion.
But I'm going this direction.
Alright, so now that we have a better idea of what is work or not, let's try a little exercise. On your worksheet, there are several different situations, and I want you to tell me whether there's work being done or not. I would also like you to explain, in a sentence or two, why or why not there's work being done. I'll let your teacher pause this video, and whenever everyone's done, we'll come back and review the answers. So teachers, I need you to pause this video whenever the word pause comes on the screen, and I'll say 3, 2, 1, pause. Are you guys ready? Alright, so in 3, 2, 1, pause. And we're back. So let's talk about the answers together, shall we? So here we have 3 situations. In the first one, the man is holding a briefcase. Now, in this situation, the force may be going up, but there's no distance, So there's actually no work being done on this briefcase. In the second situation, the man is holding the briefcase with the force going up, but the distance is to the side. Because the force and the distance are 90 degrees to one another, we can also assume that there is no work being done. In our last situation, a man is lifting a dumbbell. Because the force and the distance are both in the same direction, we can safely assume that work is being done in this situation. So now that we know about work, that it uses force and distance, let's talk about how we can do work a little bit more efficiently, using less force. So let's talk about this fun little situation.
Let's say that this man is a mover, and that he's trying to get this really heavy box onto the truck. Let's say the entire amount of work that will need to be accomplished to get the box onto the truck is 24 Newton meters. Now, let's say the distance to the truck is 1 meter. That means that the man will have to use 24 newtons of force to lift the box onto the truck, which may be too much for him. Is there any way that this man can use less force to accomplish the same amount of work? Well, looking at the equation, if we just increase the amount of distance, we can decrease the amount of force needed.
So this is where a very special tool comes into play. Introducing the ramp.
So let's say that this ramp is now 6 meters long. If we plug that into our equation and do a little algebra, that means he only has to use 4 newtons of force, which he can do easily. If we increase the distance to even more, to 12 meters, then the man has to only use 2 newtons of force, which is even easier.
So now we know that ramps, by increasing distance, allow us to do work more efficiently by using less force. Thanks to physics, you can be lazy! Yay! Alright, so let's check to see what we understand. On your worksheets again, we have several instances of people doing work. I want you to tell me, between the two instances compared, which uses less force and therefore less effort, and why. Teachers, you know the drill. I'm going to ask you to pause this video in 3, 2, 1, pause. And we're back. So let's go over those answers, huh? So for this part of the worksheet, we're looking at two different situations that use the exact same amount of work, and we're trying to determine which one uses less effort. So, if we remember, if you want to use less effort but do the same amount of work, you can use a ramp to increase the distance, which causes less force that needs to be used to move the objects using the same amount of work. So, let's look at the upper left-hand example. So this one's work is 6 Newton meters, and the force being used is 1 Newton, and it's going 6 meters. On the other side, towards the right, we also see that the work is 6 Newton meters, but the force being used is 2 newtons, and the box is traveling 3 meters. So since the one on the left hand is only using 1 Newton of force, we conclude that this one has used less effort. Now let's look at the other two examples. On the left, we have one that is using a force of 10 newtons and 1 meter distance, and on the right we have 5 newtons and 2 meters of distance, with the work both being equal in both situations, equal to 10. So again, we see that the one on the right is using less force, and therefore it is using less effort. So far we've talked about work, distance, force, and how that affects our daily lives and everything we do. But let's bring that definition of work back on the screen. Oh, thanks. Now looking at this definition, I feel like I've forgotten something important. Guess my brain's a little foggy. I should get an energy drink. Yep, that'll do her. Just need a little bit of energy. Energy! So we know that work is just energy transferred over a certain distance by a force, but what is energy? Well, funny enough, energy is defined as the ability to do work. Definitions! So in order to work, you need energy. So in order to use a force to move something over a distance, you need energy. The unit that measures energy is called joules. You mean joule? No, I mean joules. So you remember the Newton meter, right? Well, a Newton meter is actually equal to a joule. Mind blown. Yeah, we're not going to go too much further into energy because that would require a whole other episode. But just know, you need energy to do work. Okay, great. So we know all these words like force, energy, motion, distance, but what does it even matter to us? We don't even use that stuff in the real world, right? Wrong. Real world application. Oh, hey. don't mind me. Just walking around in the real world minding my own business. Boom! Used force and energy to open this door. Oh, I'm just standing here bouncing a ball. Boom! Newton's third law. Yep, just standing here not doing anything. Boom! Gravity's still a force acting on me. So you see, we use applications of work, force, motion, energy, and distance every single day. And you shouldn't take it for granted. So that's all I have for you guys today. I hope you enjoyed yourself and didn't do too much work. Ha 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 ha. Remember, stay in school and stay fly. Whoosh!
I know all about Newton, I ain't worried about nada. 'Cause I multiply force by distance and I get that product. Put in them numbers, I'ma calculate it. I know the push and the pulls and distance are related. I know you need the same direction to count it as work being done. And I'll give you some explanations of energy, force, distance, motion. Newton meters measure work, 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 work. FG equals work, 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 work. Grams help do the work, 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 work. Energy does work, 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 work. Measure work in joules. Oh, oh. Measure work in joules. Oh, oh. Let's talk about motion. Just a change in distance. We know the F equals ma, gotta thank Sir Newton. If you got a body affected by a force, then it'll move or stop moving relative to its course. But you still need the same direction to count it as work being done. And now you've got some explanations of energy, force, distance, motion. Newton meters measure work, 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 work. FG equals work, 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 work. Grams help do the work, 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 work. Energy does work, 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 work. Measure work in joules. Oh, oh. Measure work in joules. Oh, oh. Girls, do the work for me. Put it on a ramp, less force for me. Something on the ground, pick it up for me. Work 'cause FD direction the same. Doing work uses energy equal to that F times D. On my test, no cheating, 'cause I got these equations with me. If your push or your pull is 90, then you the fool, 'cause you ain't doing work. One less force, more distance, more meters, less newtons. Teach you all this to help you study. Newton meters measure work, 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 work. FT equals work, 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 work. Ramps help do the work, 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 work. Energy does work, do the work, work, do the work, 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 work. Measure work in joules. Oh, oh. 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 If you got science problem, then you don't know why you don't understand, and you wanna cry. Don't fret, my friends, because it's time for Fly Sci with Miss Sontag. It's Fly Sci with Miss Sontag. It's Fly Sci with Miss Sontag. It's Fly Sci with Miss Sontag.